Okay, good afternoon, ladies and gentlemen, and welcome to your SETI Institute Colloquium series. I'm just going to first ask you to turn off your cell phone, if it's possible. So my name is Frank Marchis. I'm a researcher at the SETI Institute, and I'm also the chair of the exoplanet group. So today I'm going to introduce you to my colleagues and friend, Christian Marois, Dr. Marois, who completed his Ph.D. at the University of Montreal in 2004. The main topic of his thesis work was to understand the limits in exoplanet imaging and to design innovating observing strategies. So Christian is basically one of these researchers who wants to image planets around other stars. After his thesis, he did his postdoctoral research at Lawrence Livermore National Laboratory and University of California at Berkeley, and then at NRC. So NRC is the National Research Council of Canada, which is a federal research institute in Canada. In 2008, while at NRC, he led the team that took the first image of another planetary system. I think most of you know the name of this beautiful planetary system called HR 8799, which has 4 planets at the moment. He used the Keck Observatory and the Gemini telescopes to do this major discovery in the field of astronomy. He's currently pursuing his research at the NRC Herzberg in Victoria, where he's part of the Gemini Planet Imager campaign. You have heard about the Gemini Planet Imager last week, a few months ago. So Christian is one of the researchers, part of this large campaign led by various institutions, including the SETI Institute. He's leading development of instruments for imaging Earth-like exoplanets using Gemini South telescopes, TMT, and also balloon-based telescopes. So today he's going to talk about a journey to Alpha Centauri and tell us a bit more how we could image an exoplanet like Earth around our nearby stars. Thank you very much.
Thank you, Frank. And first of all, thank you to SETI and Frank and Adrien for inviting me to give a talk to you guys. It's a pleasure to be here. So today I'm going to talk about Alpha Centauri, the closest star system to our own solar system. And it's a journey, so no, I'm not going to be selling tickets to go to Alpha Centauri at the end of this talk, but it's our way to be able to discover the systems of the Alpha Centauri, and if there's any planets that who knows in the future we could travel and land on these planets. So Alpha Centauri, as you know, the Milky Way is pretty big. The sun is right there, around 8 kiloparsecs away, or roughly 25,000 light years from the galactic center, and there's 100 billion stars roughly inside the Milky Way. And our sun and the stars I'm going to be talking about are right next door. So they're much smaller than the laser point there. So they're really next door. So of course, we still have a lot of road in front of us to be able to characterize all the planetary system and planets inside our Milky Way. It's a pretty big ship. It's a pretty big place. So if you look at the solar neighborhood, so we have the sun, we have the Oort clouds, the residual material from the formation of our solar system, the sun 4.5 billion years ago. And if you go to a couple of light years from us, you get the closest star system to us, the Alpha Centauri system, which is actually a triple star system, with Alpha Centauri A and B being 2 sun-like stars. So they're a little bit less massive than the sun, but they're very sun-like. And there's a Proxima Centauri, a very small red dwarf that was in the news late last year about the discovery of a potential Earth-like planets in orbit around it, which is pretty impressive given that it's very next door. And then there's a bunch of red dwarf further away. If you look at the distances, this is quite amazing. Even if they're next door, for our own distance scales, it's quite far away. If you look at, this is a logarithmic scale. If you have Earth at 1 AU, and get Saturn at 10 AU, 100 AU, you get the n roughly the solar system, and you have to go to 1,000, 10,000, 100,000 AU until you reach Alpha Centauri. So if you would like to go there, how long would it take? If you take the one of the fastest spacecraft ever launched by human, the New Horizons spacecraft that returned some quite amazing picture of Pluto last summer, you can travel. It's traveling roughly at 60,000 kilometers an hour. Sorry that I'm using kilometer. I know you guys are using miles. So it's roughly 16 kilometers a second. And it took 9.5 years to reach Pluto. So if you would like to go all the way to Alpha Centauri, it would take you 80,000 years at that speed to reach Alpha Centauri. So yeah, you have to pack a lunch to be able to get there. And yeah, so you have to have all the food, etc. So it's very complicated. It's a small spacecraft traveling at high speed. So we're not there yet. Also, the star, the Milky Way is not a static place. The stars are moving around the galactic center. They come and goes around the sun. And so this is time in thousands of years. And this is the separation, the distance between our sun and these stars. So if you look in the past 20,000 light years away, Alpha Centauri, which is the red line here, this is the binary star, and Proxima Centauri, they were 6 light years away than us. And now, today, they're roughly 4 light years away. And in the future, if you thinking that it takes you 80,000 years to reach Alpha Centauri, 80,000 years in the future, it's actually no longer the closest star to our own. It's actually moving away. And now it's Ross 128, a red dwarf, that happened to be the closest star. So it's a very dynamic place. So if you pack your lunch and go to Alpha Centauri, you need to remember that in the future, you're going to be far away from our own solar system. So the Milky Way is a dynamic place. Stuff comes and goes. And we're just extremely fortunate that currently the closest star system to our own actually has 2 sun-like stars. If you look at the distribution, the type of star in the Milky Way is dominated by this little red dwarf like Ross 248, Gliese 445, Barnard Star, Lalande 21185. These are all very tiny stars, similar in size to Jupiter. And they're by far dominating the population of stars in the Milky Way. And yet the closest ones are 2 sun-like stars. And I'm maybe a bit biased. I'm going to talk a little bit about that later in the talk. But if you want to find life as we know it, it's not clear how life can develop around these red dwarfs, these very tiny stars. But if you have a sun-like star, we know that we're here. So if you're looking for planets that are maybe similar to the sun, it's maybe more likely, similar to us, it's maybe more likely to find these type of life around stars that look like the sun. So Alpha Centauri, so what's cool about these stars, you can get out and actually look at these stars with your naked eye. They're very bright stars. Although if you go outside tonight, you won't see them because you need to be in the southern hemisphere. They're actually below your feet. But if you go to Chile, you see the Magellanic Clouds. So these are satellites of our own Milky Way. Alpha Centauri, or also known as Tollyman, is very visible, and it's sitting in the galactic plane as view from Earth. So as I said, it's a multi-planet system. So you have Alpha Centauri A. It's actually 2 stars. You have 2 sun-like stars in orbit around each other, and they take around 75 years to orbit each other. And you have the Southern Cross that's nearby as well. So if you look at the size of that planetary system, this stellar system, so if you put Alpha Centauri A at the position of the sun in our own solar system, and you look at Alpha Centauri B, it roughly goes, so you have 2 big stars similar to the sun, and they go at their closest approach around the separation of Saturn to the sun in our own solar system. So it's kind of like Star Wars. You know, this Tatooine planet, we have 2 stars in the sky. Well, it's kind of like, a little bit like that you have actually a system which has 2 stars in the sky. And of course, there's Proxima Centauri, but that one orbits very far away. That's outside of this room, around these 2 stars. So it's a system that's different than us in several ways. So us, we have one star and a bunch of planets, rocky planet in the inner region of the solar system, all the way to gas giant and ice giant in the other part of the solar system. But this system is very different. And what does it look like in the sky? So if you put A in the middle, so this is the orbit of B as viewed from our own solar system. So we're actually seeing the system very close to edge on. So the stars are moving one relative to each other. And we happen to be in a position where they're close together in the sky. And like I said, they take around 75 years to go around the system. So if you would be on one of these, on a planet orbiting one of these two stars, you would see, like I said, you would see a system that might have two suns. It would not be like this because one is further away, but that's a detail. But if you're actually on the night sky, so you're around star A and the star A go down, and you now have a night sky, well, actually, you would not necessarily have a night sky. You don't necessarily have a dark sky because you have another star in the system. And if you put the sun at the distance of Saturn, the residual light that you get around this planet is roughly the amount of light you're getting when you have a total solar eclipse. So you still have some amount of residual light and a partial blue sky. So you never have a very dark sky unless the two stars happen to be close in the sky, that you can actually have a dark sky to see other stars. So if you look at the habitable zone, so this is the region around stars where life as we knew it could potentially develop if you have the right condition. So this is a region where you could have liquid water if you have a decent atmosphere. This is the region where you would expect the planet to be to develop that kind of not biology, but ecosystem. And the size of these habitable zones depend on the star itself, its mass. If you take Sirius A, it's a very bright blue hot star. The habitable zone is very big. If you go to Alpha Centauri, these are more sun-like stars. The habitable zone gets smaller. And if you look at Proxima, which is a very tiny red dwarf, the habitable zone is tiny. So if you want to take images of exoplanets, which one is the easiest? Sirius would be the easiest, but it's far away. But Alpha Centauri, being very close, are much more variable, and Proxima is probably the last star you would actually point your telescope at because it's just too hard. Again, I'm going to come back to that later. So you could ask, well, is there a planet? Do we know if there's a planet around Alpha Cent A and B? The answer is no. We just have opportunists for now. There's no planet that's been detected. But could you form planet? Could there be planet around Alpha Cent A and B? And some scientists have looked at that in details. And the first thing that's puzzling or could be a challenge is you have two stars in the system that comes very close to each other on an ellipsoid orbit. And down to around the distance of Saturn in our own solar system. So could that second star, as it goes close to the inner system of A, could it perturb and destabilize any planet for forming or having a stable orbit? So this is what is these analyses. All the red parts, so this is separation in astronomical unit. So the Earth is around 1 AU, and you see all the red part of that figure with eccentricity, inclination of the orbit, shows that there are stable orbits around each of these stars, around the Alpha Cent A and Alpha Cent B. You can put planet around these stars and run your mathematical algorithm and check, okay, these planets are stable, they keep orbiting the star, they're not being ejected after 1 million years or something like that. So both the habitable zone around these two stars has stable orbits. The system is okay, as far as we know, that they can have habitable planets. So the second thing is, can you form planet in a binary system? You have two stars. Imagine that you have a debris disk with dust and gas. Can you form planet? Is it possible from what we know about planet formation? Even if our knowledge about planet formation is still limited, we're still learning about this process. And if we apply our state-of-the-art models about the system of Alpha Cent A and B. Again, this is separation, and you put a bunch of dust and gas, and you make this evolve with time, and you happen after 200 million years, you do have planets. These are stable orbits, and you do form planets, and they stay there. So there's nothing, as far as we know, that prevent planet from forming and having and still being there right now around Alpha Cent, but we just don't know if they're there. And also the Kepler statistics, they do have some numbers that planetary systems have been detected in multistellar system. So Kepler has found these planets, and model predict that it looks like likely. Well, it's possible to form stable planets around the Alpha Centauri system. But are there habitable planets? And what about Proxima? Well, that's actually outside the screen, I'm sorry. So of course, as you probably all learned, late last year, there was a big announcement about a rocky planet being discovered around Proxima B by Anglada, Esquede et al. NASA people were quick at putting nice poster, a very nice rendering of possible rocky planets. This is contrary to other detection. This seems a very robust detection. It combines radial velocities over a long period of time that's combined even further away data back in time that's still fully consistent. So it's really, this is real. It's a big deal. It's quite exciting. The radial velocity signal is quite strong. The orbit is around 11 days around the star. So again, the star is very tiny. It's an M5 star, a red dwarf. The radius, a tenth of the stellar diameter. The mass is around 1.27 Earth mass, which is amazing in terms of, but it's still the minimum mass of the planet. It could still be a slightly more massive, and it's receiving roughly 65% of the amount of energy that Earth is receiving. So if you compare the system with the sun, so you have the sun, you have Mercury's orbit here to scale, and you look at Proxima B, the star is very tiny, and the habitable zone sits at a fraction of the distance of Mercury's orbit. And the planet is roughly at the inner edge of the habitable zone around Proxima B. So there were a couple of papers after the discovery about the challenges. Okay, people have found solutions, but it's still debated in the field if you can actually, if this planet could be habitable due to several issues. The first one is the planet is almost certainly tidally locked. So the planet is always facing the same size of the planet is always facing the star. The star is flaring. They have small flare that are 60 times a day. You have huge amount of UV and X-ray radiation coming up from the star. It's a very active star. And you have 8 mega flares, so there's a big flare that the star could get a 50% or plus brighter, which could be a challenge to form life. You have very strong winds, which could blow away the atmosphere of the planet. You have a very red spectrum, so the color of the star, as viewed from our eye, is probably a salmon-like reddish color. So you can ask question, could you have vegetation around these? And if yes, what kind of vegetation would use for the red spectrum instead of the green, like Earth? The planet almost certainly did not form there, so it maybe migrated to that current location. How do you get water to that planet is still a challenge. It's sitting very close. It would have to form further out to get some water and then migrate it inward. It's kind of cold. It's receiving less light than Earth. And who knows? We don't know fully the orbit of the planet, of the star itself. So you might have some gravitational interaction with the other two stars in the system. So it's challenging. Some other issues. So with time, a star do evolve. So they tend to be very bright when they're young, and evolve with time. So the habitable zone is actually changing position as a function of time. And Proxima B, at the beginning of the system, here, when the system was very young, if it was at that location when the system formed, it was actually outside the habitable zone, and it only got in after several 100 million years inside the habitable zone around the star. And so it's still unclear what kind of planet is Proxima B. The very nice MOSE spacecraft, it's a space photometer, analyze the star and detect flares. People have looked for transit. There was a nice paper by Kipping et al. They tried to see if they could see the planet transit. If it transit, it opened up a huge amount of possibilities to do characterization of the atmosphere of the planet, but sadly it wasn't detected. They had a couple of tentative signal, but they don't match the planet, and they're not sure if they're real or something else that's generating fake transit. So the fact that it doesn't look like transiting does offer some challenges. How are we going to be able to characterize this planet in the future? So some people were already published paper about possible ways to do this. One will be to use a James Webb Space Telescope that's going to be launching very soon at the end of this year, next year, 2018. And if you take 10 micron images in the thermal light, and you do a very long campaign, you could see the phase of the planet. If it's tightly locked, there's one part that's very warm, the other part is very cold. And as the phase change, you could actually see the phase curve of the planet, and that would be able to do some amount of spectroscopy and derive biomarkers with that, but that's still a very large amount of James Webb time to secure to be able to do this. The VLT instrument in Chile, one of the 4.8 meter, they're upgrading an instrument called Expresso that they want to combine with SPHERE and look for the planet with high resolution spectroscopy, but that's still around 300 hours, and that's beyond 2020. So that we still have a couple of years to wait before we can see the result of these attempts. And with the 30-meter class telescope coming online in mid-2020s or closer to 2030, people are already thinking about specialized instrument with 10 hour of 30-meter time, which is very small compared to James Webb and others. You could potentially see the planet orbiting the star and be able to do characterization as well. So still challenging, so you guys will have to wait a couple of years for astronomers to develop the technology and instrumentation to be able to characterize this planet. So stay tuned. People have tried to find planets around Alpha Centauri A and B, but it's much more challenging. The fact that the stars are much bigger, much warmer, much more massive, mean that all our current technologies to see planets are less efficient. So there was a claim by JWST et al. In 2012 of a planet Alpha Cent B around the star B, but it turns out that after further analysis by the other team that this is actually not real. So there's no planet orbiting, currently no planet orbiting Alpha Cent B. There was a follow-up to try to see the transit of this planet. They actually did not see it, but they did see a signal that could be a transit, but they're not fully sure if this is real or not. So the jury is still out to figure out if there's planet around Alpha Cent A and B. And the current limit from the radial velocity campaign is we know that there's no Neptune mass planet or above, Neptune mass planet or more massive around any of the two stars. But what about imaging? So let's say you want to take images of planet around Alpha Cent. How would you do this? So people over the years have managed to take images of planet around other stars, but these are usually gas giant planets like the H3799 system. We have four to seven Jupiter mass planets that are in orbit around the stars. You got 51 Ari, one of the very nice Gemini Planet Imager discoveries. Again, it's roughly a 2 Jupiter mass. You have Beta Pic, around 10 Jupiter mass, and 1609, which is again a 10 to 13 Jupiter mass object. So if you want to go down to habitable planet, what does it take? So to give you some perspective of how hard it is to take images of habitable planet, so let's take Mount Everest. This is something we all know. and some people might have traveled there. So let's assume that the size of the age of the mountain is the amount of light being emitted by a star. And let's say you're looking for a gas giant planet like Jupiter, but a young version of a gas giant where it's still bright from its recent formation. So what you're looking for is a football field, lost on Mount Everest. So you're looking around for a big football field, and this is what a young Jupiter looks like. So this is what has been done so far for HR-799, 51 Beta Picturesque. This is the football field lost on Mount Everest. If you want to look for an old Jupiter planet, so instead of seeing this in thermal light, you're seeing the planet in reflected light, which is much harder. You're actually looking for a baseball. So that's getting harder. So you imagine you're walking Mount Everest looking for a baseball. So if you're looking for an Earth-like planet in reflection light, so how many people here gardens during the summer or winter? Here, you guys have a summer all year long. You're actually looking for this little red spider. So you're looking for this spider lost on Mount Everest. Good luck. I won't be part of your expedition. But that was for reflected light. And if you change the color of where you're looking for that planet, that can have a very dramatic impact on the contrast or what you're looking for around Mount Everest. So the reflected light, usually what people talk about is in the visible, where you have roughly a 10 to the 10 contrast, which is 10 billion to 1. But if you go instead at 10 micron, this is the peak emission wavelength of the Earth. The Earth is roughly a 280 black body, roughly speaking. And at 10 micron, the Earth is actually the brightest object in the solar system. And the contrast with the star is actually much more favorable. If you look at the distance between this curve, this is the Earth as in reflected light, and the sun, this is 10 to the 10 contrast. If you look here, the Earth at 10 micron and the sun is actually 10 to the 7 contrast. It's 1,000 times easier to see a rocky habitable planet at 10 micron than it is in the visible. So this is the 10 micron approach to detect habitable planets around other stars. At 10 micron, the Earth looks like this. There's no phase because there's a lot of wind that moves the heat around between the day side and the night side of the Earth. So it looks like a roughly uniform black body. The dark region are actually clouds, which make the planet look colder. But the size you're looking for, again, is this big football field around Mount Everest. So now it's much more easier. So instead of a little red spider, it's a big football field. And also, you could ask, well, what can we learn about doing this 10 micron imaging? There's actually a very nice sets of biomarkers at 10 microns. If you do spectroscopy, so this is wavelength, this is color, with intensity, you see there's water, there's methane, there's ozone, something that protect life on Earth from the deadly radiation from the sun. You have CO2 as well, which could be a sign of activities or volcanism. And also the shape of that curve tells you you can have a rough idea of the surface temperature of the planet. Since you're actually looking or detecting the radiation being emitted by the planet, you learn about its surface condition, and have a rough idea how well you guys could like living on that planet. But really the key thing is the contrast. It's much more easier to detect than in reflected light. So then you could ask, well, when I was working on this, I was thinking about TMT, because there's a huge advantage of doing this on a 30-meter telescope. But then I realized, could we do something on a 10-meter telescope, something we can do now, because we have access to these 10-meter telescopes. So if you take, again, Alpha Cent A and B with their habitable zone, and you put our limit of diffraction, this is the limit of our telescope where we can actually distinguish between two objects. At some point, if they're too close, their light starts to blend, and it's impossible to see that planet. So the telescope needs to be big enough to be able to separate these two objects. And this is the size of diffraction. So this is the limit of our telescope. So for both Alpha Cent A and B, our current 10-meter telescope are big enough to make this happen. So we could develop an instrument now to point at Alpha Centauri, A and B, only these two stars in the sky where you could actually do this. And you could be sensitive to rocky planets like Earth, which is amazing when you think about it. So we started this project called TIKI. So it's called TIKI because originally it was meant for Mauna Kea and the 30-meter telescope. But then we realized, well, we could do something now. We can build a small prototype and go test all the technology at Gemini South in Chile and point this instrument on Alpha Cent A and B and be able now to detect these habitable planets. So Gemini South is near La Serena in Chile, very nice site. So we started working on the instrument. So we need to be careful with thermal imaging. All your instrument in your telescope glows. The Earth is at 280 Kelvin, your mirror is at 280 Kelvin, and you're looking for a 280 Kelvin object. So all your telescope and your optics are light bolts. So the more you have warm surfaces in your optics, the worse it gets. So we need to minimize the amount of warm part in the system, and you put everything cryogenic. So it's a very tiny instrument. It's something that could be assembled in a few years. And we use the latest technology called a Vortex coronagraph. This is a system where you block the starlight to be able to see a planet that's very near the star. So there are some in California and in Europe. There are people that specialize in developing this kind of coronagraph, and they've been tested on sky, and they actually work. This is extremely good to be able to detect objects that are very near, that are very faint, and very near very bright objects. So when you're trying to do this, you're also limited by the telescope that are imperfection. Optics are as little ripples, and they produce what we call lookalike of planets, but they're not planets. They're just residual effect of your instrument. We also call them speckle. So I have a student working on this concept that was developed by a French group, where you have your star in the middle, and you need to be able to modify the light. So you're basically playing music. It's like you're modifying, playing with light, so that it fully cancels out to produce what we call a dark hole, where you can actually see your little planets. So this is a very powerful technique where you could reject all the starlight and have the contrast, the sensitivity to see these habitable planets. You also need an optimized observation strategies. And due to an innovating young Ph.D. student a decade ago, myself, we actually invented this very efficient observing strategies called angular differential imaging. So this is Keck data. The star is in the middle. You see there's a lot of light coming from the star. And if people have very good eyes, you could actually already see a planet around that star. It's actually right there. And this filtering, so this technique, this observing technique, is using how the telescope has been built to basically save money. They're all attitude azimuth telescope. And when you track an object in the sky, the images are rotating, and you can devise algorithm to reject everything, all these little lookalike planets. They're going to stay roughly fixed with time, and you can write software to reject that light and keep what's rotating with time. So it gives you an idea what it looks like. So this is the planet. You see the planet spinning around. This is after subtracting the star. And when you pile up the data after an hour, you see that there's actually 4 planets. This is H3799 that appears from the data. So the gain here from there is a factor 100. So having the instrument, the observation strategies is critical to be able to get to that kind of contrast. And late last year, a collaborator and I, Jason Wong, decided to use all these images that we done of H3799 and done an orbital motion movie. So you can see the planets are moving like the Kepler laws. Kepler was right. So planets in the inner part move faster. This one's orbit in 50 years. This one is roughly 400 years. Again, 4 gas giant planets. But we could imagine doing this kind of animation and detection around Alpha Centauri, but instead of being gas giant planets, they could be habitable planets. We also developed innovating post-processing technique. As I told you, when you're trying to see these planets at 10 micron, all your optics are bulbed that are emitting a lot of light. So we invented new techniques that give you roughly 3 times better subtraction of the background, which basically boosts your efficiency by a factor 10, which is critical to be able to get to that level of contrast. So if you put all this together, and then if you would point a fully optimized instrument toward Alpha Centauri, what it would look like. So if you have 200 hours of telescope time, this is what it looks like. So this is star B. This is star A. And you know this little bimp of light right there? That's a rocky planet exactly like Earth orbiting Alpha Centauri A. So this is showing that current technologies, all your instrumentation, observation strategies could get you down to these rocky planet with such instrument. So it's right there. So what about the future? So this is with a 10-meter telescope. What could we do with this instrument on a 30-meter telescope? That's 3 to 4 times bigger than the current telescope and almost 10 times the flux. And these instruments should go up, should be built in the next decade. So as I showed you, so this is Alpha Centauri A and B, and this is a planet, an exo-Earth at 1 AU, Earth size. It's a copy of Earth. This is with an 8-meter telescope. So with a 30-meter telescope, it would look like this. So so you have a detection of Earth itself. You have Venus. You can barely see Mars, and you see Jupiter. So going from an 8-meter telescope to a 30-meter telescope is an enormous gain of sensitivity. An Earth would be detected in 5 minutes. So people that are at 3 sigma, so people that are going to be able to assemble this 30-meter class telescope and put that 10-micron imaging camera underneath, going to be able to revolutionize the field in a matter of weeks. It's that amazing. So we need these 30, 40-meter telescope as quickly as possible so we can do this. And of course, the instrumentation that comes with it. So if you ever find a planet around Alpha Centauri, and especially with a 30-meter telescope where you have a very good detection in a short amount of time, what can we learn about this planet? You can derive, of course, as I said, there's a lot of biomarkers. There's ozone, there's water, there's a CO2, methane. You can detect clouds. You can potentially see season variation. You can derive the surface temperature. So there's a lot of characterization you could do at 10 micron. But it's not all. As I told you, with a 10-meter telescope, you can only do 2 stars in the sky, Alpha Centauri A and B. But if you build this instrument for a 30-meter telescope, you can access a lot more systems. So of course, so this is the resolution limit. So this is the limit of what we can do with a 30-meter telescope. So this is separation, various amount of stars. The green region are the habitable zone where you could expect to find planet like Earth. So a 30-meter telescope, Alpha Centauri A and B are easy. Then you can have other stars that are further away. You can do Epsilon Eridani. You can do Procyon, that has a white dwarf. You have a binary star, 61 Cygni A and B, Epsilon Indi A, Tau SETI has known rocky planet in orbit around it. They are being detected by what we call the radial velocity technique. But with the 10 micron imaging camera, we could actually take pictures of these planets in a decade from now. And also Gromebridge is another star. So you guys should expect that with this right instrumentation, that in the next decade we'd actually start taking images of these rocky planet that's been discovered by other techniques. So can we do this now? Well, it turns out that compared to the previous generation of thermal imaging cameras that were built in around 2000, they now have a new generation of detectors that are much more sensitive than what we had before, by almost a factor 2, which is a big deal when you're talking about 100 hours of telescope time to be able to detect these objects. A factor 2 saves you 50 hours of telescope time. You can now build infrared cameras to do all this. In terms of contrast, the amount of contrast that you need to detect this planet is comparable to what we get right now with the Gemini Planet Imager or Sphere. So it's basically the same amount, roughly the same technology, but you just apply it to 10 micron. We have better thermal background, which is essential to get as deep as possible to see these planets. We have optimized observation strategies. We have telescope time from the observatory. So what we remain is to have this instrument. But the funding, we're still working on it. It turns out that it's not easy to fund this kind of instrument because you're building a fully optimized instrument for current 10-meter telescope for 2 stars. And it's a fishing expedition. We don't know if there's something there, but if we don't look, we'll never know. But you have to look also at the long run, is if all the knowledge that you're going to have from having this instrument on a 10-meter telescope, you can then bring this technology to these 30-meter telescope, where you can actually do a survey of 10 to 15 stars in the sky. And so it's now much more interesting, and it's no longer zero. We'll have the capabilities of actually imaging and characterizing other Earth in the next decade. So our team is pretty big, so people from around the world thinking and hoping to get this started as soon as possible. So in terms of conclusion, right on time, so Alpha Centauri is not a focus of trying to find these habitable planet. People are developing technologies, instruments to be able to do this as quickly as we can. Proxima B is a very interesting candidate, but for direct imaging, it's impossible right now. We have to wait to James Webb or the ELT, the 30-meter telescope, a decade from now. And Alpha Cent A and B, the 2 sun-like stars, so we could actually detect now these planets with the right instrumentation and right telescope. Thank you very much.
Thank you, Christian. The floor is open for questions. Okay, one here. Let's start this side.
Hi. So my understanding is that at the current configuration, from our point of view, Alpha Centauri A and B are fairly close to one another, and that's a problem. I understand how the technology works per star, but how do you deal with the light from the companion star?
It's a very good question. That's something we need to simulate more. For 30-meter telescope, it's less of a problem because the images of the stellar light is going to be sharper, so you less contamination toward the other stars. For thermal imaging, also the contrast being a lot less than what you need is less of a problem as well. Also, we have 200 hours of imaging, so the secondary is going to move quite a bit, so the signal is going to be averaging out. So it's still work in progress, but it's I believe this is a lot less of a problem for us than, let's say, the radial velocity technique that are trying to detect the planet by the barycenter motion, and where they get always contamination from the B stars that get into their fiber and make a mess.
Jack?
What capabilities will the EELT first generation instruments have for imaging Alpha Centauri for planets?
Oh, that's a very good question. So what kind of instrumentation the TMT will have, the ELT will have to take images of Alpha Centauri? The answer is none right now. What we're hoping is to develop this technology as a visitor class instrument. So at first light, the facility class instrument are given that they need to make everybody happy in the TMT and ELT consortium. The first generation of instrument is to make the most people happy. And so developing and putting money on an instrument that does 10 stars at the thermal infrared is probably not the most popular instrument for a general use group of astronomers. But the teams are pushing hard, so I'm only one team at Gemini. There's another team pushing at the Magellan and GMT. There's another team pushing at the EELT in Europe, and we all pushing for this to make this arrive at the telescope as soon as possible. As for first to second generation instrument, The EELT does have the MITSIS instrument that could potentially do this, but it's probably a year or two after first light. So I think EELT are probably the one that's the best organized right now to get this at the telescope as soon as possible.
So how much does the TIKI instrument cost for a 10-meter telescope, and how much more expensive does it get for that kind of instrumentation when you go up to the ELT or TMT?
So we haven't yet worked out the price for a TMT instrument, but we're working at finding the right price for this 10 meter. The current estimate we have is around 5 million. So it's, you know, it's not, if you compare with the Gemini Planet Imager that costs 25 to 30 million, but the GPI is a facility class instrument. This is a small prototype basically. So we only have one mode of observation. We try to keep stuff as simple as we can. And also the fact doing an extreme AO instrument at 10 micron is actually much easier in some way than doing it at 1.6 micron. You don't need these deformable mirror as big as what we need for GPI. Everything can be smaller and more compact. So we're estimating at around 5 million.
Would you have any comment on the Starshot or the technology?
Yeah, so Starshot, that's a project from the Breakthrough organization that want to send little credit card probe that are launched at 20% of the speed of light. I think it's a very innovating and challenging project. But if we ever find these planets around Alpha Cent A and B, they would be prime. I would be quite interested if they could send some of these probes toward Alpha Cent to take surface images of these worlds. I think it's Starshot, if they can make it work, there's still a lot of challenges for this to make it happen. But it's on our lifetime, it might be the easiest way or the fastest way to try to get surface images of these exoplanets.
So I have a question related to this. Could you show the slide again where you discuss what we will know from the planet based on the spectroscopic studies and what kind of information we will derive? Could you comment a little bit more on this part?
Okay, well, like I said, the nice thing about direct imaging is you're actually seeing the planet light, so you can track its position as a function of time. So you can derive its orbit. This is important because if the planet has a very eccentric orbit and it goes very close to the star, that's usually bad to find life. So but if it has a mostly circular orbit like the Earth, then it's probably more likely to have a stable environment to be able to have life to develop. The surface temperature, this is critical to, if we want to have an idea if the surface has a roughly 5 degrees Celsius average like the Earth, doing spectroscopy and starting to fit black body to these emissions gonna tell you about the surface properties. Ozone is believed to be a must to protect life to develop on its surface to block the UV radiation coming from the star. You want to see water in the atmosphere. That's usually, we believe it's a must to have so that life can develop. CO2 is usually a sign of activity, volcanism or other. Methane could also be linked to biological activities. So there's a degeneracy between cloud and radius, but if you make some assumption of how much cloud covering you have on the planet, you can actually derive its radius. So you don't have to have transit or other technique to derive the radius of the planet. You can actually make a direct estimate of the planet's radius. But you do need a 30-meter telescope to be able to do this, because every time the flux drop, it's also dropping our atmosphere, because we're looking to our own atmosphere. And if the throughput goes down, it means that the background goes up. So it's harder for us to remove the thermal background for us to see the planet. So it's a problem from observing. When you're looking for, it's hard when you're looking for something that is the exact match to where you are. Our atmosphere gets in the way.
So what about a balloon?
Yeah, so Frank and I have a small project for a balloon telescope, but this is more about the prototyping and testing space technologies. For the thermal infrared, having a balloon would probably be impossible because you don't have the telescope aperture to be able to resolve your system. You would need a 10-meter balloon telescope, which is probably crazy. But if you develop the technology for the reflected light, then you need a much smaller telescope. And Russ Billikov at NASA AIM has a project to build a 75-centimeter space telescope to look at Alpha Centauri A and B for, multiple years. So to look for reflected light of rocky planet. So if you look for the reflected light, you could imagine doing something like this on the balloon as well. NASA has these very stable, long-duration balloon flights, and you can imagine putting a meter-class telescope on a balloon for 3 months and do a campaign. And there's a Picture C project in the United States that's been funded to start this technology, but we're also starting this technology in Canada for us to gain some experience and hopefully grow the project where we could have maybe two systems on balloons trying to make these reflected light detection.
Now, what is the technology advancement in infrared detectors that's given that improvement of a factor of 2 in sensitivity?
Oh, that's a very good question. So the oldest generation of detector were, these are old Aquarius arrays, I believe, with a QE around 40%. And their new detector are MCT based, so different kind of substrate, and the QE is believed to be around 80%. So it's a factor of 2. Beside that, I'm not a detector expert. But it's pretty, if we really can confirm this gain in sensitivity on the detector, that's a major big deal for us, especially for this 10-meter project.
Okay. Oh, there's one more question over there. Sorry.
So I assume to really get the most out of a 30-meter telescope, you need really good adaptive optics. Can you just comment on what the limits of adaptive optics are, what the challenges are, and how that impacts what we can do?
I think that the biggest challenge is to make astronomers happy. Because everybody's pushing toward their field. Adaptive optics on 30-meter telescopes are not very different than 10-meter telescopes. You just need more actuators. So the systems are bigger. The nefarious adaptive optics system that NRC, my institution, is building and designing for TMT is the size of a truck, and with optics that are that big. So it's really, the bigger the telescope, the bigger the instrument, the more expensive they become. But the fundamental technologies are not that different.
So it's a mature technology, we just need to scale it up.
Yeah, exactly. So it's the scaling up problems, and that comes with that. And then astronomers want a big field of view. Our field want a very good correction and a tiny field of view, but other astronomers want a wide field, medium correction. Some people want to do this at K-band at 2.2 microns, so they want the AO system to be cooled down to make sure that it doesn't generate any background in their detection. So it's really figure out how to build this to make everybody happy. And has the other question, the first generation instrument, giving the big potential of TMT, they're trying to make as many people happy with the first generation. And our field being a very tiny field in astronomy and a very focused application, well, it's hard to figure out a way in that system. So I think trying to get funding from elsewhere to be able to build these instruments to make sure that we're ready at first light and can approach TMT or other ELT and say, okay, look guys, we have this camera, it's ready to go. And the 10-micron camera is probably the best camera you could imagine to debug a telescope, because the image quality is already very good from the start. And we have an extreme AO system, so we can do correction, we can look at the segment or all phase, and they want to look at bright star, we're interested in bright star, so it's a very good match to debug a telescope. So we're hoping to get that angle in, but it's still up in the air how that's going to work out in the end.
Now, at 10 microns, isn't the primary mirror emitting all kinds of radiation at 10 microns? How do you avoid that?
Yeah, so like I said, you're totally right. Telescopes, all the optics that are warm are glowing at 280 Kelvin, basically. So that's why you need big telescope and a lot of integration time to average that light coming from the telescope. The atmosphere as well is glowing at 280 from residual water band in the atmosphere. So in contrast wise, to just see the planet against the star residual light, it's actually, the technology exists already. So it's really then why it takes 200 hours or 50, it's between 50 and 200 depending on the instrument configuration. But that huge amount of time is to remove the thermal light from the instrument and atmosphere. So it's just averaging images over 200 hours or 50 hours.
Okay, well, Christian, apparently until we find this $5 million, we're going to have a lot of discussion and enjoying a lot of tea and coffee. So this is the mug that you're going to get as a memory of your talk here.
Thank you.
Thank you very much for coming here. Thanks. Thanks a lot.